All right, this is the second half of section 9.3. So the first half was simulations. Now we're going to get into something that's related to probability and often mistaken for probability, and those are odds. So odds and probability are often used interchangeably, those terms, and they're really different, okay? And it's really not a huge difference, but they are different, okay? A probability, compares your chance of winning or losing to the total number of possibilities. So like a 2 out of 10 or a 1 out of 6 chance. The odds compare your chances of winning or losing to each other. So it's not a total. So if you see the odds are, say, 1 to 40, that's not a probability. That's not 1 out of 40. That's one way of winning, 40 ways of losing. Okay, so they are different things. They are both kind of related to chances, but they are totally different things. So let's suppose that the odds in favor of Fat Chewy winning the Wiener Nationals. You guys familiar with the Wiener Nationals? It's a wiener dog race where little wiener dogs compete in a little race. It's adorable. It's absolutely adorable. My mom always had wiener dogs when I was growing up. We always had beagles and wiener dogs. And she had one. His name was Chewy, and good God, that dog was fat. So fat. And yeah, we used to joke that we should enter him in the Wiener Nationals. That dog he would chase some food. That's why it was fat. Anyway, so let's suppose Fat Chewy here, may he rest, that his odds of winning are 1 to 40. This means that of every 41 races, so this is your total for 1 and 40. Okay? For every 41 races, Fat Chewy is expected to win one of them. And that's pretty much if the other dogs just don't show up or, decide to, run off in the other direction. And he's going to lose 40. So this is the number of ways to win, the number of ways to lose. Together, they make up the total. But probabilities, if you have like a 1 out of 40 probability, then that means one way of winning, 40 total. This is not the total. This is winning to losing. So the odds in favor are the number of favorable, in this case winning, outcomes to, so the word to here is often used with odds, to the number of unfavorable outcomes. In this case, we mean losing. The odds against is just the reciprocal of the odds in favor. So the odds against Fat Chewy winning are 40 to 1. We often use the word to here, T-O, for odds. Now, odds and ratios can be written with this word, to. We can use a colon, or we can write it as a fraction. The thing I don't like about writing as a fraction is that then it gets really confused with probabilities. So I prefer personally to use these two. However, my lab sometimes chooses to use this. So I just want you to know that all three are acceptable. I tend to prefer one of these two just to keep them visually separated from probabilities so that you don't get the two as confused. Now, if the odds in favor are 1 to 40, the odds against is the reciprocal, 40 to 1. We do have a formula here that can convert between odds and probabilities. So let me scooch that up. Now, if we're converting from odds to probability, what we can do, if the odds in favor are n to m, then the probability in favor is n over n plus m. And the probability against is m over n plus m. Now, this sounds like a hot mess over here. If you just remember that odds are, the two parts together make up your whole, right? N and m together add up to be your total. See, there's your total. Probability is out of a total. The probability in favor, well, it depends on which odds you are. If you're the odds in favor, then favor is first. So that would be your top number. if the odds in favor, favor's first, unfavorable is second. Now, if you have a probability and you're converting it to odds, that's a little trickier here. That one's probably going to use, the formula a little bit more. But going from odds to probability isn't as bad. So if we've got a probability that something occurs, remember we have the complement, the A bar here. That's the probability that A does not occur. Let me grab a highlighter here. Grab some pink. Remember the not, that complement right there. I'm going to accent that complement so that we can all see what it is. The odds in favor is the probability of favor divided by the probability of not in favor. That's the unfavorable. By dividing these two, the total is going to be the same for both probabilities because they have the same sample space. So those totals, those denominators are going to divide out, and you're just going to end up with a ratio of favor to unfavorable, or vice versa. These formulas are probably easier seen than said. So I'm just going to kind of leave these here, and I will flip back and reference them as we use them. Okay? So if you're looking at these and you're like, no, don't flip the page, I don't get it, I'll be back. Promise. Okay, so you roll a fair six-sided die. Let's find the probability of rolling a 4 or a 5. Okay, we can do probabilities. A 4 or a 5. Those are two outcomes out of a total of 6. So the probability is 2 out of 6 or 1/3. Find the odds in favor of rolling a 4 or a 5. All right, well, I've got my probability. I can use either one of these. That's why I left both of them circled here. The odds in favor, right? I've got my probability in favor. That's the probability of A over the probability of not A. All right, so I'm going to take the probability of 4 or 5 divided by the probability of not 4 or 5. The probability of getting a 4 or 5, we have 1/3 from up here. The not is the complement. That is the rest of your total. And for probabilities, we know the total is 1. So the rest of that total is 2/3. Together, these make up 3/3, or 1 whole sample space probability. Dividing these two fractions, 1/3 divided by 2/3, if you wanted to do the whole thing out, you multiply by the reciprocal of 2/3, and you get 1/2, or 1/2. That means that the odds in favor of rolling a 4 or a 5 are 1/2. There's one way for a 4 or 5 to show up for every 2 ways for it not to show up. I used the 1/3 and the 2/3 business here. I could have used 2/6 and 4/6. That would have given me a 2 to 4, meaning there's 2 ways to get a 4 or 5 out of 4 ways to not get a 4 or a 5. So remember, the odds in favor compare the favorable, the ways for it to happen, to colon, T-O, the ways for it not to happen. Now, once you have the odds in favor, the odds against are easy. It's just the reciprocal. So that's just going to be 2 to 1. So probabilities compare a part to a total. Odds compare winning to losing, or favorable to unfavorable. Or in this case, it was the odds against, so it was unfavorable to favorable. All right, what are the odds in favor of flipping a fair coin and it landing on tails? Well, what's the probability of landing on tails? The probability of it landing on tails is 1/2. Okay. So the odds, we can come back to this formula. The odds in favor would be the probability divided by the complement probability. Remember, that was the not. So the odds in favor would be the probability of tails over the probability of not tails. Now I could use tails with a bar over it. Just sometimes my bars, you can't see them because of the fraction bar, so that's why I'm just choosing to write out the word not here. So the probability of tails is 1/2. What's the probability of not getting tails? Well, that's heads, which is still 1/2. If you divide this out, you get 1. So how do you write those odds? Well, it's, 1 is still a fraction. It's 1/1. So we say that these odds are 1-to-1. Anytime you have a 1-to-1 odds, that means that the two outcomes are equally likely. The favorable and the unfavorable outcomes are equally likely. I shouldn't say two outcomes. The favorable and unfavorable are equally likely. We're used to 1/2 being equally likely, right? When it comes to two things, one or the other. But as far as odds go, that means that those two things, tails and not tails, are equally likely. All right, so let's go down here and let's find the odds in favor of drawing a king. Now what we can do, if you don't want to use the probability, we could do that. We could do the probability of a king divided by the probability of not a king, if you wanted to do that division. We could also do the number of ways to get a king, colon, the number of ways to not get a king. So you could skip the division, because really what the division does is it just gets rid of the denominator. Because when you multiply this fraction by this reciprocal, those 2's go away. When I multiplied that top fraction by its reciprocal, those denominators of 3 went away. So if you choose, you could do it that way. And I don't tell you that to confuse you. I just want to give you, all the information. Just in case you're thinking, well, hey, what if I did this? Is that still correct? Absolutely. I love when you guys think like that. I love it when you guys say, well, I'm thinking about doing it this way. I love that. I love doing things, in different ways to, encourage you guys to think for yourselves. Okay, so we can do the probability of getting a king over the probability of not getting a king, or I could do the number of ways to get a king, or in this case, the number of kings, two, colon, the number of ways not to get a king. I'm going to abbreviate that since I'm running out of space. Okay, how many kings are in a deck of cards? Well, there's 4. So how many ways are there to get a king? 4. So it's 4 to how many cards are not kings? Well, there's 52 cards in a deck. If 4 of them are kings, the rest of them are not. So that would be 48. Now, you could leave that as 4 to 48. Okay? That's perfectly fine with me. I'm not sure my lab is going to like that. You should reduce this because this is a fraction. Remember how we said that you could write it in any of these ways? This colon is the same as a fraction. So you can reduce that, just like you would 4 over 48, and get 1 out of 12. Or sorry, 1 to 12. I shouldn't say out of. That makes it sound like a probability. So 1 to 12. If you did this using the probability, you would have gotten 4 out of 52 divided by 48 over 52. The 52s would have canceled, and lo and behold, you would have gotten 4 over 48, which reduces to be 112. Okay, the odds against drawing a card that is both a 7 and a club. Now, because it says against, that's the number that needs to come first. Right? So you can do this by probabilities if you wanted to, and say the probability against getting a 7 and a club. So you could do the probability against over the probability of 7 and club. Now notice the not is on top here because the word against was first. So let me just accent that a little bit here. Because the word against was first, the not went on top. Up here, the word in favor was first, so the favorable went on top. So remember over here, favor, favorable on top, against, the not was on top. You could also do this by counting like we did up here, the number of ways to not get a club. I'm going to go back to the probability here. Okay, so how many cards are a 7 and a club? Well, there's just one, the 7 of clubs. So there's just one card out of 52 that is a 7 and a club. So there's that probability. That means the ones that are not 7s and clubs must be the rest of the deck. When you divide these, those denominators are going to cancel, and we're going to get 51 over 1. So that gives me the odds against as 51 to 1. It is very important that you pay attention to whether or not it's the odds in favor or the odds against. Okay? So if it's the odds against, then that probability of not goes on top. If it's the odds in favor, then the favorable goes on top and the not, the complement there, goes on the bottom. Okay, there's a 40% chance of snow today. What are the odds against snow today? This is a probability. Okay, when I say there's a 40% chance of snow, that's a probability. So the probability of snow is 40%. Now let me just ask you something. How is it that probability is 40% when in the couple sections ago we said that probabilities were never bigger than 1? That's because 40% is smaller than 1. It's a percent, so it's a decimal. It's 0.4 or 0.40, however you want to write it. So as far as the numerical value of it without the percent sign here, it's 0.4, so it is smaller than 1. Now what does that mean as far as the complement goes? What is the probability of not snow, or snow bar, the complement? If the probability of snow is 40% or 0.4, what is the probability of it not snowing? Well, that must be the 60% or 0.6. So the odds against, you got to pay close attention to what word comes first. The against, the not comes first. So that's the probability of not snow divided by the probability of snow. So that's going to be 0.6 over 0.4. Now that is going to simplify. So if you take 0.6 divided by 0.4, you can move those decimals over and get 6 over 4, which reduces to be 3 over 2, which gives me the odds of 3 to 2. Now, you just so you know, you can do that on your calculator, just in case I lost you there. If you wanted to do 0.6 divided by 0.4, you get 1.5. Go to math, change that to a fraction. There you go. So just don't want you thinking there's some kind of mathematical witchcraft happening here. Okay, so if the first number of the odds in favor is much larger than the second, the probability is close to 1. The probability in favor, that is. If the first number is much smaller, then the probability is close to 0. So, with that being said, which wiener dog has the best chance of winning? So here's your list of puppers, and there's your odds in favor of them winning. So take a second, pause the video, look at those numbers, and tell me which one of those dogs has the best probability or the best chance of winning. Okay, so if the odds in favor, if the first number is a lot bigger than the second, then probability is close to 1. That means it's close to being certain. All right, second number is bigger. Ooh, first number is bigger. But is it much larger? I mean, it's more than double. Nope. Oh, 25 is much larger than 2, especially compared to 5 to 2 here. And here we got Mr. Skippy here with 1 to 1. So it looks like, as far as these odds go, 25 is much larger than 2. So as far as the odds in favor go, Butters has the best chance of winning. Okay? So Butters has the best chance of winning because his probability is going to be 25 over 27. That's his probability. His odds are 25 to 2. That means for every 27 races ran, Butters is going to win 25 of them and lose 2 of them. Which dog has the worst chance of winning? Well, that's going to be Flash here. Flash has a 1 to 100. 1 chance in favor of him winning, 100 ways to lose. Every 101 races, Flash is going to win 1 of them. And remember this 1 to 1 business, how we said that means it's kind of a 1, that was a 1/2 probability. So Skippy, he's a 50-50 shot, right? 50% chance he'll win, 50% chance he'll lose. Maybe Skippy will skip across the finish line, maybe he won't. So, fun facts here. Racetracks use odds for betting purposes. Okay, so I'm about to teach you how to gamble. But the odds that racetracks give you are the odds against. Okay, so the last list I gave you the odds in favor. So the odds in favor of Flash winning were 1 to 100. That means that the odds against are 100 to 1. Okay, so I gave you the odds in favor because those tend to be more easy to understand, in the beginning. But as far as like racetracks go, they're going to give you the odds against. So the odds against Flash winning were 100 to 1. Now, let me just tell you how this translates to you gambling. This means that if you bet on Flash and she won, you would win $100 for every $1 you bet, plus your bet back. That means if you bet $20 that Flash would win, and then she won, you would get $100 for each dollar you bet, plus your bet back, plus your money back that you bet. You would win $2,020. Now, if the track gave you accurate odds, spoiler alert, they don't. Just like Vegas does not give you, accurate odds and stuff as well. Then over a long period of time, your expected value would be 0. That means your wins and your losses should balance out to be 0. We know that's not the case, right? Because racetracks and casinos and stuff like that, they're in the business of making money. They're not in the business of being fair and breaking even. Now, what this means, this expected value formula, I'm going to explain in the next page here, but $100 won for every dollar. The probability of winning was 1 out of 101. Remember, because her odds were 1 to 100. The dollar that you lose, associated with the probability that you lose, if you add this up, you get 0. What that means, this expected value means that your wins and your losses will even out over time. Now, expected value, if the expected value, I'm going to give you a formula for it, but I just want you to know that if it's 0, then the game, or whatever you're doing, is fair. If the expected value is positive, and you're calculating it from your perspective, then it benefits you. If the expected value is negative, that means that you're losing money, it benefits the house. Now, I use that in quotes. I don't know if you've heard that terminology before, but when referring to like casinos or something, and they talk about the house, that means that the casino wins. If you're playing blackjack or something, if over time of, sitting at a blackjack table, if the game is fair, your wins and losses should even out to be 0. It's not. It's going to be negative. It's going to benefit, the casino or the racetrack or wherever you are. Now, something we need to go ahead and establish right now, because this happens every semester. If something benefits you, it's not fair. I've heard people use the phrase, "Oh, well, it's fair to me." That doesn't make sense. What do you mean it's fair to you? No. Fair means fair to all parties involved. If it benefits you, it's not fair, because that means that it's benefiting you and not somebody else. So I just want to go ahead and establish that, because it feels like every single time I teach this class, that question comes up. So I figured I would go ahead and discuss it in case you were thinking it. Okay, so the expected value is the average winnings or losses over a long period of time. It is not useful for predicting a single outcome. Our formula looks like a hot mess, but basically what it is, it's all the probabilities multiplied by their corresponding values. So if you have a probability of a specific event or a specific outcome, and that outcome has a value associated with it, of a win or a loss, and you add up all those. Now, see how these are smushed together? That means multiplication between those probabilities and values. That's a V. I know people usually ask me why my V's look like that. My variable V's look different than my letter V's. All right, so example 8. So let's use an expected value here. A 5-card hand is dealt from a standard 52-card deck. If the hand contains at least one king, you win $10. Otherwise, you lose $1. Is this game fair? Now, we have to go ahead and establish something right now. If I ask you, is a game fair? This is not your opinion. Okay, I'm not asking for your opinion. I'm not being like, yeah, it sounds fair. No. I want a mathematical answer. The word fair has been mathematically defined for you up here. So this is, and a lot of times like on tests and stuff, I will say, this is not your opinion, justify your answer with mathematics. So I want you to find the expected value and tell me, is this game fair or not? So, why does this camera make my nails look all yellow and gross? They're not. Why is that? I don't know. I'm over here, I can see them on my computer and I'm like, gross. Am I looking like I've been digging in some earwax or something? Anyway, so is this game fair? Anyway, back at the home front here. Need to adjust the white balance on my screen, maybe it'll be better. So we have basically two situations here, right? You get a 5-card hand. Either it's got a king or it doesn't. That's only two options. So let's find the probability of getting at least one king. Now, the probability of at least one is 1 minus the probability of none. Because the opposite of at least one is none. So because those two are complementary events, they add up to be 1. So if I move that negative over here, I get, this plus this equals 1. So at least one king, 1 minus, what is the probability of not getting a king? Oh, okay, this is about to be really messy, okay? Because this is a 5-card hand. This is a multi-stage event. Oh, does that sound familiar? It should, because it's from the last section here. This is a multi-stage event. 5 cards are dealt, no replacement. The first card is not a king. There are 4 kings in the deck. That means 48 cards are not kings. Okay, that's your first card. We got 5 cards. The next card, not a king. Now we're down to 47 cards that are not kings out of 51 cards. Now we got 46 out of 50. How do we know when to stop? I'm sure you see the pattern by now, but where do we stop? Well, I'm running out of space, so there's that. But fortunately, that's all I need. 1, 2, 3, 4, 5 cards. This one is terrible, okay? That's why I chose to do this one, because you've got this at least one business in here where you have to use that 1 minus the probability of none. And you've got this multi-stage event of 5 cards. Okay, so if you do this computation, you get 0.3412 as that probability. That is your probability of winning. That's the at least one king. Okay, so that's your winning. So that would be the value of $10 associated with that probability. Okay, so my expected value is going to be the probability of at least one king times the value of winning plus the probability of not getting a king, and that's your losing value. I think I've pretty much successfully written that so small that you can't read it. The expected value is a probability, so this is the winning probability, winning value. Losing probability, losing value. All right, my winning probability here was that 0.3412. They're not all this terrible, okay? I just picked a really nasty one just in case you stumble upon one. The winning value is $10. Now, what is my losing probability? That's the probability of getting no king. That's this multiplication right here. So that's my 0.6588. And that value is losing $1. Now notice how I put a negative right there because I'm losing that money. This is positive because I'm winning that money. All right, where did I get this number so quick? These two numbers are going to add up to be 1. You could multiply all that out and get the 0.6588, or you can just subtract this from 1 and get the 0.6588. Either way, I'm going to multiply those together, I'm going to multiply those together, I'm going to add all that up, and I get barely enough room here, 2.75. So, is it fair? No, because it's not 0. If the expected value is 0, then it's fair. It's a positive number, so this game benefits you. Okay? God, I had to pause the video because my dog's out in the hallway scratching. I just hear thump, 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 thump. I go out there to yell at my kids, keep it down, and it's the dog. So anyway, this being positive means that it benefits you. So back to my question, is this game fair? No. Now remember, this is not a yes or no question where you just get to guess. Like, yes, no, I don't know. You have to provide me some mathematical justification here. So it's no, because $2.75 is greater than 0. Okay? All right. Last page. A game involves you rolling a fair 6-sided die. You win the number of dollars coinciding with the number facing up. That means if you roll a 6, you win $6. You roll a 3, you win $3. Is this game fair? Well, notice you don't have to pay anything. So it kind of feels like it's not going to be fair, right? It feels like it's going to benefit you because no matter what you do, you're going to win. We have 6 outcomes because you win the number of dollars coinciding with the number facing up. Okay, so here's what we're going to do. The expected value, we've got rolling a 1. The probability of rolling a 1 is 1/6. The value of rolling a 1 is you winning $1. Rolling a 2. The probability is 1/6. The value is $2. Rolling a 3. Rolling a 4. Each one's got the same probability. And I can already tell I'm going to run out of room. Of course I am, because I write really big and fat and then I squeeze everything in. And then we get 1/6 times 5. That's for rolling a 5. And then we have 1/6 times 6. I could have wrote this a lot nicer by just saying 1/6 times 1 plus 2 plus 3 plus 4 plus 5 plus 6. And that's going to be 7 times 3 is 21 over 6. All right, what kind of witchcraft just went down there? You guys know, you can add those up quickly, right? The Gaussian method, 6 plus 1 is 7, right? Pair of 7, and then there's 3 pairs. All right, so 21 over 6. Let's see, what does that end up being? That ends up being 3.5. Now, because we're talking about money, so is this game fair? No. It benefits the player. Because 350 is positive. Okay, now, let's rework this. What if you pay $2 to play? You have to pay $2 up front. Now, is it fair? Again, this is not a yes or no question. This is not your opinion. All right, let's go through these 6 expected values again. Or sorry, these 6 outcomes again. You roll a 1. Probability of rolling a 1. What is the value of rolling a 1? Well, you win $1, but you had to pay $2. So the overall value of rolling a 1 is how much? Well, if you roll a 1, you win $1, but you had to pay 2, so you are down $1. Okay. Then we have rolling a 2. If you roll a 2, you win $2, but you had to pay $2, so now you break even. If you roll a 3, you win 3, but you had to pay 2, so that's only a $1 gain. If you roll a 4, you're going to win 4, but you had to pay 2, so you're going to net $2. If you roll a 5, you're going to net $3. And if you roll a 6, you're going to be on the positive $4. Again, we can take out that 1/6 that's common and add -1 plus 0 plus 1 plus 2 plus 3 plus 4. That ends up being 4, 5, 6, 7, 8, 9 over 6, which is 3/2, so it's 1.5. Nope, still not fair. Still benefits you. Now, you could do this another way. You could, look, notice how this changed. This really just went down by 2. So, yeah, you can just, if there's no cost to you in the beginning here, you can just take that and subtract off 2, because you know there's a 100% chance, you know, a probability of 1 that you're going to have to pay that in order to play. So you know that's going to be subtracted off. So that's no coincidence right there. So here's the question. Without doing a bunch of guessing and checking, how much must you pay in order for this game to be fair? Well, let's look back to right here. That is what's whispering the sweet nothings into your ear and telling you how much to pay. Okay? So when we didn't have to pay anything, it benefited us by $3.50. So if we paid $3.50, that would make the game fair, or the expected value 0. So let's scooch this up. So let's look back at part A. Now, if you looked at part B and said, oh, well, I need to pay $1.50, yeah, in addition to the 2 you've already paid, gives me the same answer of $3.50. So we need to pay $3.50 in order for the game to be fair. Now remember, the word fair means that it's just as likely that you will win as lose. It means that your wins and losses will balance out over time to where nobody is monetarily benefiting. Okay? You nor the house. That's what it means to be fair. So I don't want you to accidentally think, oh, well, this benefits me, so yeah, it's fair. No, it's not fair. Because if it's talking about you playing a game with a friend, now that means that that friend is consistently going to lose. Not fair for them. So fair means fair for all parties involved. So here, let me just kind of quickly highlight this so that you don't look back and say, where did she grab that number from? Right there. Okay, at long last, I know this has been a very long section. I don't know why this book does this. This used to be 2 separate sections. The simulations were one and the odds were another. They're just throwing so much stuff together into one section. It is ridiculous. And that just is a continued theme in this edition of this book. So, all right, I'm going to stop rambling because it has been 45 long minutes. I hope you have enjoyed learning about Fat Chewy and Butters and the Winter Nationals and how to gamble and basically not to gamble because it's not going to benefit you. No. Anyway, that's the end of section 9.3.